So, dear colleagues, it's time to start today's morning session. And the first speaker is Yuji Hashimoto sensei from Japan. And he will speak about improved supersingularity testing of elliptic curves using legendre form. Please.
Thank you for the introduction. I'm Yuji Hashimoto from the University of Tokyo. And this is joint work with Koji Nuida. I'm not good at English, so I'm sorry if I can't answer some of the questions from the participants. In this presentation, I explain the contents of this slide in order from the top. Elliptic curves can be divided into ordinary curves and supersingular curves. Supersingularity testing, which determines whether an elliptic curve over a finite field of characteristic P is a supersingular, is an important tool for using cryptographic protocols. There are two types of supersingularity testing algorithms: probabilistic algorithms and deterministic algorithms. For practical purpose, probabilistic algorithms is used. However, probabilistic algorithms cannot prove that a supersingular elliptic curve given as input is indeed a supersingular elliptic curve. The deterministic algorithm is slower than probabilistic algorithms. Instead, it can prove that a given supersingular elliptic curve is indeed a supersingular elliptic curve. In this research, we focus on deterministic algorithm. Here, I explain the contribution of our research. There are two contributions. First, we reduced the cost of power root computations by almost half, which is a dominant cost. Second, we constructed a simple algorithm by using the fundamental Legendre map and the lambda switching theorem. I briefly explained the preliminary mathematical knowledge needed to explain supersingularity testing. Here, I explain the symbols used in this presentation. Let P be a prime number greater than or equal to 5, Fp be a prime field, and Fp bar P be an algebraic closure of Fp, and Fp square be a quadratic extension field.
It was off on you.
Okay. Next, I explain the overview of isomorphic graphs. Isomorphic graphs is the graph in which the vertices consist of isomorphism graphs. Okay. Next, I explain the overview of isomorphic graph. Isomorphic graphs is a graph in which the vertices consist of isomorphism plus of elliptic curves and the edges corresponding to isogenies. From the next slide, we will explain elliptic curves and isogenies. First, I explain elliptic curves over Fp square. A non-singular algebraic curve E with genus 1 defined over Fp square is called an elliptic curve defined over Fp square. since the above definition is abstract, we explain a concrete example of an elliptic curve. For example, this curve is a Weierstrass curve. Next, we explain FP relation point of elliptic curve E of this form. Let OE be the infinite point of the curve E, then FP relation point is the set of XY satisfying this equation and the union set of OE. The above set is a group by operation between the point. Therefore, FP relation point is also called FP relation point group. Suppose this equation is factored in this way. Then we call 0, 0, gamma 0, delta 0 two torsion points. In this slide, I explain isogeny, which is the edge of isogeny graphs. Isogeny phi of elliptic curves defined over Fp square is a surjective morphism of curves that induces this group homomorphism. For L not divisible by P, a separable isogeny is called L isogeny. If the kernel phi is isomorphic to Z over Lz, let's see the subgroup of order 2 on an elliptic curve E, then there exists a unique 2 isogeny phi. Okay, I'm going to explain the two-Boltzmann graph. Explain the graph structure of isogeny graph over Fp square. A graph that the vertices are elliptic curves and the edges are isogenies is called isogeny graph. The graph of ordinary curve over Fp square has a graph structure called the Boltzmann graph, and the isogeny graph of supersingular over Fp square has a graph structure called the Ramanujan graph. If we can know whether the graph structure is Boltzmann graph, we can know the type of elliptic curve. I'm going to explain the two-Boltzmann graph in detail, but you don't need to know everything exactly. You can see that the shape of the graph is usually at a mountain shape, like the figure in this slide. And two-Boltzmann graph is a connected undirected graph whose vertices are partitioned into levels V0, Vh, we call H height. This is an example of two Boltzmann graphs of height 2. V0 is the top of the volcano here. And V1 is V1 is here. So at the bottom of this volcano, V2. Okay. In fact, there are a few conditions for the two-Boltzmann graph. V0 is a connected regular graph of degree 0, 1, or 2. For I greater than 0, at each V in Vi has exactly one neighbor in Vi minus 1. All edges not on V0 arise in this manner. For I smaller than h, each V in Vi has degree 3. Okay, I explain overview of existing algorithms. If if E is ordinary, and the two isogeny graph is two volcano. If we choose three non-backtracking paths from the initial vertex, at least one of the paths is descending on the two isogeny at the volcano. For example, if the given elliptic curve is this vertex, then if we compute the isogeny three direction extending from this vertex, this edge is descending edge. Height of two volcano graph are less than or equal to log 2p plus 1. This symbol is flow function. At least one of those at least one of those edges of V in VH is out of volcano graph. Okay. I explain testing method. Let J be a J invariant of an elliptic curve. In ordinary case, if a vertex J on volcano graph, J in FP square, and if a vertex J on out of volcano graph, J not in FP square. On the other hand, in supersingular case, all vertices on supersingular isogeny graph are in FP square. We will explain existing algorithms. First, we explain about Sutherland algorithm. And draw a graph by isogeny computations using iteratively modular polynomial and check whether or not it is a volcano graph. Let R be a square root and M be a multiplication, and I be inversion and C be a constant multiplication. The cost per step of modular polynomial computation is 3R plus 9M plus 15C. Okay, we explain Hashimoto-Takashima algorithm. Draw a graph by isogeny computations using iteratively two torsion points and check whether or not it is a volcano graph. Let R be a square root and M be a multiplication and I be a inversion and C be a constant multiplication. The cost per step of the computation is 3R plus 3M. However, it is an algorithm with such a prime condition. We explain our proposed algorithm. Draw a graph by isogeny computation using iteratively at only the two torsion point lambda of legendre curve, and check whether or not it is a volcano graph. Let R be a fourth root and M be a multiplication and I be a inversion and C be a constant multiplication. The cost per step of the computation is 3 over 2R plus 3M plus 3I plus 3C. Square or fourth root computations dominates in supersingularity testing algorithms. I note that the computational time for square root and fourth root computation is almost the same. I will explain this fact later. We reduce the cost of power root computation by almost half which is the dominant cost. We explain ideas for improvements and preliminaries. The key idea behind the efficiency of algorithm is to use some properties of x coordinates lambda of two torsion points in Legendre curves and isolates between elliptic curves of the form. Legendre curves are of this form. Here, lambda is not equal to 0 or 1. In this presentation, we call the important parameter lambda Legendre parameter. Any elliptic curve with a characteristic other than 2 can be transformed to a Legendre curve. I explain important property of Legendre curves. X coordinates of two torsion point of supersingular Legendre curve is lambda all lie in FP square. By using this fact, lambda can be used as a condition for determining whether an elliptic curve is a supersingular curve. Okay, let A be two elements in FP square such that B is not equal to 0. A squared minus 4B is not equal to 0. There is a two isogeny phi of this form. This elliptic curve, the EAB divided by 0, 0, EAB over 0, 0 is expressed as here. Okay. Let gamma 0, delta 0 be two torsion points of elliptic curve EAB, and phi gamma be a two isogeny mapping from EAB to EAB over gamma 0. We can compute E divided by gamma 0, delta 0, and by using phi. By using this fact. The EAB over gamma 0 and EAB over delta 0 is expressed as follows. We explain our technical contributions. Legendre curve E lambda is an elliptic curve of the form EAB. There is a two isogeny phi mapping from E lambda to E lambda over 0, 0. E lambda over 0, 0 is expressed as follows. We can obtain E lambda over 0, 0 by using phi. Let 1, 0, lambda 0 be two torsion points of elliptic curve at E lambda, and phi 1 be a two isogeny mapping from E lambda to E lambda over 1, 0. And phi lambda be a two isogeny mapping from E lambda to E lambda over lambda 0. By using two facts, we can compute E over 1, 0, lambda 0 by using phi. The E lambda over 1, 0 and E lambda over lambda 0 is expressed as follows. In this slide, I define fundamental Legendre maps phi 0. Before that, we explain how to transform this elliptic curve into a Legendre curve. The transformation from this elliptic curve to Legendre curve, this Legendre curve can be done by letting Legendre parameter lambda be alpha over beta. E lambda over 0, is expressed as follows. And therefore, the Legendre parameter of this curve is the square root of lambda plus 1 squared divided by the square root lambda minus 1 squared. We defined a map phi 0 whose input is Legendre parameter of E lambda and output is Legendre parameter of E lambda over 0, 0. In the same way, I defined the fundamental Legendre map phi 0 and phi lambda. E lambda over 0, 0 is E lambda over 1, 0 is expressed as follows. Therefore, the Legendre parameter E lambda 1, 0 is the square root of 1 minus lambda plus 1 over square root of 1 minus lambda minus 1 squared. The Legendre parameter E lambda over lambda 0 is square root of lambda at minus 1 plus the square root of lambda over the square root of lambda minus 1 minus square root of lambda squared. We define a map phi 0 phi lambda whose input is Legendre parameter of E lambda and output is Legendre parameter of E lambda over 1, 0 and E lambda over lambda 0. We want to investigate the structure of isonic graph by iteratively computing the fundamental Legendre map. We want to use only phi 0 whenever possible because phi 0 is the simple representation among those images of fundamental Legendre map. But phi 0, phi 0, phi 0, phi 1, phi 0, phi lambda are backtrack. We propose a solution to this problem. To iteratively compute isogeny by using only phi 0 without backtracking. We propose lambda switching. Let's KBR 0, 1 or lambda. Then 1 at phi 0, 1 at 1 minus phi 0, 1 minus phi k lambda is non-backtrack. We can draw isonic graph by using iteratively computing 1 minus phi 0, 1 minus phi 0 lambda instead of phi 0, phi 0 lambda. Let lambda be a Legendre parameter. E lambda is isomorphic to E1 minus lambda. For the above reason, lambda and 1 minus lambda can be switched. We can compute two fundamental Legendre map 1 minus phi 0 lambda, 1 minus phi 0, 1 minus phi 0 lambda by computing V only. Okay. Okay, I will explain our proposed algorithms. Okay, step 1, we compute the two edges in 3 directions of a given elliptic curve E lambda. That we want to check whether E lambda is a supersingular curve. Let lambda I mu be the legendre parameter in the mu direction. For each direction, mu equals 1, 2, 3, we iteratively compute step 2 and step 3 from I equal 1 to log 2p minus 1 over 2. Step 2, we compute 1 minus phi 0 lambda I mu and 1 minus phi 0, 1 minus phi 0 lambda I mu. Step 3, if 1 minus phi 0 lambda I mu not in fp square, or 1 minus phi 0, 1 minus phi 0 lambda I mu not in fp square, if lambda is ordinary. Step 4, if lambda is not determined to be ordinary, then if lambda is supersingular. Let lambda 1 1 equal defined lambda. This condition for 3 direction, we compute the following legendre parameter and check the whether this element is in fp square. Let be at the fourth root lambda I mu. Then for each direction, we compute the following. Step 3. Step 3, we okay. It's if 1 minus this here or 1 minus here not in fp square, then E lambda is ordinary. Step 4, E lambda is not determined to be ordinary, then E lambda is supersingular. Okay, we investigate the computational time of square root computation and the computational time of fourth root computation of legendre parameter lambda. Fourth root computation would be almost the same as the computational time for square root computation. We also investigate the performance of Sutherland algorithm and the performance of our proposed algorithm. The computational time of our algorithms was improved to almost half of that of Sutherland algorithm. Okay, we reduce the cost summary. We reduce the cost of power root computation by almost half, which is dominant cost of supersingularity testing algorithms based on isogeny graphs. We construct a simple algorithms by using the fundamental legendre map and the lambda switching theorem. This completes the presentation. Thank you very much.
Thank you very much. So there is time for a couple of short questions. Please.
My first question is about the definition of a volcano graph that you are using. It involves a partition of the set of vertices of a graph. Could you please comment a bit on that partition? Can it be just arbitrary partition, or do you have any assumptions on that partition?
Okay, volcano graph.
Yes, your definition of volcano graph. So just a graph with a given partition of the vertices into levels. So are there any assumptions at all on this partition, or can we use just any partition?
Sorry, please, once more, please.
Yes. Do you assume anything on this partition, on the partition that is involved in the definition of a two-volcano graph? Is the partition arbitrary? Okay, I'll just, never mind. Well, I will check with your paper. But then my second question would be, could you please go to slide number 37? Slide number 37 in your presentation.
Okay.
Right. So what we see here in the topmost formula is actually just the second iteration of the map 1 minus phi 0 applied to lambda, right? So it's a composition of, it's the square of a map. You apply phi 0 to lambda, you take the negative of that, you add 1, then you do the same with the result. Does it make sense to look at higher iterations of this map? So what happens if you do this once again? You apply phi 0, you take the negative, you add 1. Does it make sense in your theory? Well, maybe you could just give us a reference to your paper when the result is published. We can double check.
Sorry.
Okay, sure, yes. Thank you very much.
Thank you very much.
Maybe somebody in Zoom have a question? Well, if not, let us thank the speakers again. And we now proceed to the second talk. So please,
yes, it's
please repeat your talk. Yeah.
So first I try to share my window.
Yeah.
And where is to share? Here looks, and then probably this PDF file is better, I think. So
yeah, that's it.
You see the screen of mine.
So could you please make it full screen?
Yes, I already shared my window, but
no, but full screen. Control L.
Full screen.
Yeah.
Yes, it's right.
Yeah. Okay. I think we can start with this.
Okay.
So,
yeah.
And
I think the larger the.
Yeah. Larger.
The characters are quite large now. So the good morning. First of all, I want to express my thanks to the conference organizers for inviting me to give a talk. And the title of my talk is on geometric property of Fermat-Torricelli points on the sphere. This is a joint work with Yu Chen, Xiang, and Wang Yuzheng in my department. So next page is the outline, the contents of the talk. So first I will give some introduction to the problem. Then I will tell some results about numerical experiments. And then we tell how to transform the geometric problem to the algebraic problem, so which we will use the metric equation. And then the fourth step is the sketch of solving the algebraic equation. Then we will see something about the geometry property of the points we are discussing. Finally, we show some solved problems. I not go to the next page. Yeah, yes, this is the next page. So here we see one unit sphere, and if we take, I think we miss something. Oh, we miss too much. Here, this is a correct place. So this is an introduction to the problem. So we see there's a result of Fermat which says if give you a planar triangle in the plane, a triangle in the plane, if we try to find the point in this plane, so that the sum of the distance FA plus FB and FC is minimal, then either these optimal points lies at one of the vertices, or these three angles are equal to 120 degrees. So this is the condition. If all angles of triangle ABC are less than 120 degrees, then F is inside the triangle, and which is called the isogonal point. So the similar problem was discussed for sphere. Here, if we are given 3 points A, B, C on the unit sphere, we want to find the point F so that the geodesic, the sphere distance, this curved AF plus BF plus CF is minimal. This problem was discussed by Gallier and Haji. The result was very beautiful. It's very similar to the plane triangle. But if we change the distance between the points FA, FB, FC to the usual Euclidean distance, which means you just connect 2 points and take the section of the line and measure this length, then this problem is relatively difficult. And this page shows a result of Gallier and Haja. So we just go to the next picture, which was for the Euclidean distance. For the Euclidean distance, if we are given 3 points A, B, C on the sphere, then we try to minimize the sum of the distance between F, P, PA, PB, and PC, which we written as UVW. Then this problem can be transformed to one nonlinear programming problem, and the result, the minimum of L, the sum of the distance, was connected with A and B and C by one algebraic equation of degree 12 in this form, which is very complicated. So in this talk, we want to investigate what is a property, geometric property of this optimal point P. So this we just shows property again. So these are some non-results. So if this angles, one of the angles is larger than 120 degrees, then the minimum point P will be coincide with this one of the vertices of A, B, or C. This is one non-result. Another one is if we draw a plane through these 3 points, A, B, C, then the plane will cut the sphere into 2 spherical caps. Then the minimum point P must be on the smaller part, and another point that satisfies the distance between QA, QB, and QC. The sum is maximum, then Q must be on the larger part. This is relatively easier to prove. And then we see some numerical experiments. The procedure is first we construct a small square and cubes of this quantity, 1/64. These are very small squares and cubes. We use a lot of this kind of point set to cover the unit sphere. Then we generate some data set. So the first data set is data set 5, which is composed by this 5 tuple A, B, C, D, E, where A, B, C are selected from the various combination of this very small square and cubes that's used to cover in the unit sphere. If we fix A, B, C, then we calculate which small cube or square contains the minimum point, which square or cube contains the maximum point for the sum of the distance. Then we use all this kind of data to form a data set we call the data set 5. And another data set is generated by this way. This data set is composed by 4 tuple A, B, C, D, where A, B, C are selected from the various combination of the initial squares and cubes that's covering the unit sphere. And we, after fixing A, B, C, we check which D. D is also some kind of square or cube, so that this dA plus dB and dC are maximum. Here we see that ABC are selected from the initial cubes for covering the equator. So this is a special point. So then this is not difficult for computer to do this. Then we found the data set 5 contains this the cardinality of this data set is 9.79 million. And data set 4 is only 128,000. So these are numerical experiment. Then we find something from this fact, from this data set. So using computer, we find this approximate fact. If angle A, angle B, and angle C are all not greater than this number, 120 degrees, then the minimum Fermat-Torricelli point and D for that minimum point, E for maximum point, the distance between these 2 points are always approximately 2. This is very surprising, but we have not proved this result yet. This is the first observation. For the second observation is that if angle A, B, C are not greater than here when n is missed, greater than not greater than 120 degrees, then we have this property. This dA, dB, and dC here, this the length of these 3 sections are approximately same. The ratios are same. So this is also quite surprising. And in this paper, we actually not proved these 2 results yet. The another empirical results from dataset 4 is for a lot of cases, the maximum point D, a minimum point D, which I means the distance, the sum of the distance dA plus dB and plus dC is minimum. Assume A, B, C are on the equator. If this sum is minimal, then depends on the position of A, B, C. Sometimes D is on the sphere, on the this surface part of the hemisphere. And sometimes this D is simply lying on this equator, So here I draw a picture. If the HB and the C are in this red area, then this maximum, this point, maximum point is on the equator. If B and C are in this blue, dark blue area, then if in this dark blue area, then the point D is on this equator. If it's in the red part, then it's in the this surface of the hemisphere. This is something we are going to see in this paper. So we go to next page, and this page will show how to construct equations for this kind of problem. Sorry. So here we use a kind of metric equation, which says if n plus 2 points, n plus 2 arbitrary points is selected from one n-dimensional Euclidean space, then this determinant equals to 0. This was because of this determinant actually decide the volume of the simplex formed by P1, P2 to n plus 2. Here is n plus 2. For 5 points, we here show a smaller picture. Here in 3-dimensional space, if we take any 5 points, P1, P2, P3, P4, and P5, then we take this as a simplex of in 4th-dimensional space. Then the volume of the simplex is 0 because these 5 points are actually selected from the 3-dim space. So this determinant equals to 0. So this result was established by Kellermanger in long time ago. So we will use this to construct algebraic equation for our problem. So we will see for our problem. So here we try to explain equations for, here should be five points on the unit sphere. If we take A, B, C, P on the unit sphere, then we have AB equals to C, BC equals to A, CA equals to B, and this X, Y, Z. These are A, B, C, P 4 points. Then we take another point O as the sphere center of the 5th point. Then the distance are all equals to 1. Then apply the metric equation. We will get this, this actually, which is a polynomial of A, B, C, and X, Y, Z. So this is for 4 points because we take another points O. So here, if we consider O, then it's 5 points, but only 4 points on the unit sphere. Then we see for 3 points on the equator, then we have the simpler polynomial. Here, assume A, B, C are 3 points on the equator, and the little A, B, C are distances between these 3 points. Then we will have this determinant equals to 0. So if we expand this determinant, then we will get this kind of polynomial. This is from the metric equation for 4 points in 2-dimensional space case. So then almost here we can construct our nonlinear problem like this. So the objective function is x plus y plus z, and the constraint condition is f1a bc xyz equals to 0. So this here this polynomial was obtained by the resultant of f minus 1 f0. We eliminate a from that, then we get this kind of condition. So then we see next page. So then we use the Lagrange multiplier method. This is all people know, so we just go to next page. Then we get the system of polynomial equations here, F5a, which was obtained by this computation, and the F6b is from this. Then we get this F5a, F6a for solving the nonlinear programming problem. Then we see these are three, F1a, F5a, F6a. If we can solve x, y, z from these three equations, then we will get the result of our problem. So we go to the next page. So this page will show some strategy to solving the equation. So first we do before this we eliminate a from the non-condition. Now we can also eliminate b and c from that equation. So we will get 9 polynomial equations here. So actually 3 are enough, but if we get 9, then probably it's better we can help us to solve the equation system. So here just to show how to use the Sylvester resultant to eliminate one variable from 2 polynomials. So this is very classical result. We just go to next page. Then we show some paths of elimination. So there are a lot of smaller, simpler polynomials obtained. We will not show this in detail here because it's already probably only 5 minutes left. Then we go to see, we get a proposition 2. Then this is to say the solution, the original polynomial equation systems can be simplified to this larger system under the condition h1 not equals to 0. If h1 of ABC is not equals to 0, then the original equation system can be simplified to this system. So then we go further. The next result is if we can construct another polynomial Q, which is bivariate polynomial. If H1 of ABC and the Q of BC, Q of CA, Q of AB not equals to 0, then the original equation system can be simplified to this here, this very simple form. This almost linear system. Then we see this proved already the main result of our talk. This we proved if ABC are from the equator, P is satisfying this sum is maximum, then either P is on the equator 2 or P lies in the interior of the hemisphere set minus the equator. with satisfying this quite simple condition. So this is equivalent to this linear form from last page. So then we have some remarks. So first, in general, the point on the sphere that satisfies the linear condition doesn't lie on the equator. This can be checked by numerically. And the second remark is, if this H1 of ABC not equals to 0, then also this point ABC are selected from the equator. Then we have always 2 points P and P prime satisfies the linear condition we showed last page. So this one, this condition, there are always 2 points. One is P and another is P prime. We can also select get 2 antipodal points on the sphere, Q and Q prime. So this is the 2 remarks. And then further problems is we try to find the polynomial or equations that divide the red area and the blue area. But this is not solved at this moment yet. So I think this is the last page already. Oh, another problem. Another further problem is if we allow ABC arbitrarily selected from the unit sphere, then we define a point P that satisfies this condition. We conjecture this point P, the point P satisfies this condition is also kind of Fermat-Torricelli point. This is also not solved because of the polynomials were too complicated when we use Maple to do computation. So thank you very much for your intention and
thank you very much for your interesting
thank you.
presentation. Are there some comments or questions? Yeah. Please.
What would be the applications, your results, for example, when building geographic maps and so on, or maybe something else?
The kind of minimize distance sum from one point to some non-points in the plane was useful because if you try to set up some something which you need to minimize the cost, looks useful. But for the sphere, though the Earth is sphere, but the scale is too large. So I think for sphere, this problem looks only for curious investigation. Looks, yet we didn't find any meaningful application yet. But we will we will read more literatures to see if there's any meaningful application. Thank you. We also think this problem very often, but we didn't find a good reason to explain.
Thank you.
Oh, thank you. Thank you. I hope people will also try to using other algebraic system to solve that polynomial equations. And I recommend the metric equation very much, which I feel it's useful to transform the geometric problem to algebraic form.
Yeah. There are other questions?
Is this approach extendable to higher dimensions? What about the sphere in dimension 4, for example?
Oh, we were not dare to do this computation. Probably just that would be if people can find some new way to do hand reasoning by human brain to do something, then probably we can get some breakthrough. Otherwise, seems in 3D that already too complicated computation. So it's always object too large things of that when we use Maple or Mathematica to solve the equations we constructed. So I hope people can find the fourth dimension result in some good way.
So just a comment that I know my colleague, we are Michael Monaghan's PhD students. He's working on faster algorithms on polynomial system solving. Yeah, especially the resultant. So I hope he can get some breakthrough and
oh, good. Thank you.
Okay, maybe there are other questions from Zoom participants. So if there are no further questions, then let's thank the speaker again.
Thank you again for patience.
Now we have coffee break till 11 o'clock.
Yeah. Thank you.
Hi, Ioannis. Do you hear me?
Hi.
Okay, hi.
I hear you.
Victor, I'm chairing this session, so could you please try to share your screen?
Yeah. So I have an Acrobat reader.
Please.
Okay. I have an Acrobat reader.
Okay.
So now you should be able to
it's
see
visible. Okay, great. So.
Okay. Is it good though? Maybe.
Yeah, full screen is better, of course. Yeah.
Well, I can use full screen. Full screen mode, right?
Yeah.
Okay.
So you will give this talk, right?
Exactly.
Okay, thanks.
So what is the plan? First of all,
no. It's not time yet at 11.
Yeah, I know. But what's the plan? So maybe I will use 50 minutes to have some time for questions at the end.
It would be perfect, but also 55, I guess, is okay.
Yeah. Okay.
Good.
So Timur, is that you?
Please.
So is it Timur? Are you Timur?
No. I'm Victor. You don't know me, probably. Timur.
Yeah.
Is
Okay.
here.
That's why.
Yeah.
Because I know Timur, but you are using his. Are you using his? I see. Okay.
He's here. Yeah, but he's on coffee break.
Yeah, sure. Okay. But you're using his. He speaks her.
Yeah.
Yeah. Okay. Good. Because I. So you're Victor. Okay. Good. Okay, Victor.
Okay.
Yeah. Okay. The thing is, Victor.
So it's time to announce the second distinguished invited lecture of this conference. which will be given by Ioannis Emiris, who is the President and General Director of Athena Research Center. Please.
For introduction, let me share my screen. Do you see my screen?
Yes.
Good.
Maybe
okay.
Now it's better.
Now it's full screen. Yeah, now it's better. Okay. So I'm very glad to be here, and I thank you for the invitation. It is a pity that we're not physically together, but I'll try to give you an idea of our work, and I'll be happy to take questions at the end. So recently I took up some more administrative duties by taking the leadership of Athena Research Center. This allows me to have more time for building on collaborations and building on projects and applied research. I remain a professor at the University of Athens, where I do my more mathematical research. So today I'll talk about a topic that is joint work with two students of mine, PhD student Evangelos Bartzos and master student Charalambos Tzamos, who is here. Both of them are ready to finish their degree. So the topic has to do with a problem that comes from combinatorics. I'll talk a lot about graph theory today. It has a lot of nice geometric applications because you see already the picture from bioinformatics. And it has, of course, a lot of algebraic modeling and a lot of polynomials that allow us to get information about what is happening in this problem. It's a problem from the physical world. And the physical world can be at a microscopic scale, like molecules, or it can be at a macroscopic scale. So let me give you some examples. So it can be at the macroscopic scale if it comes to questions in architecture, like the third picture here. I don't know if you can see my mouse on the transparency. So this is an architectural structure that has stability, and it includes bars, but also includes tables. So today we talk about distance problems where we specify distances, like these bars. Of course, when it comes to tables, we only have an upper bound on the distance. We don't have the precise distance. And as the title suggests, I'll try to combine and I'll try to address these problems by using tools from algebraic geometry, such as bounds on the number of roots for polynomial systems, multi-homogeneous polynomial systems, to be more precise, and such tools from computer algebra. The first example comes from robotics, is the famous Stewart platform. Some people call it Gao platform. You have two rigid bodies connected by 6 legs. And the only control we have is on the length of the legs. And by specifying the length of the 6 legs, we control the positioning and the orientation of the end effector. So because we are in free space, there are 6 degrees of freedom for the position and the orientation of the end effector. So we need 6 controls. The connections are free to move and to rotate, but we can control the length of the 6 legs. Okay, this is a very famous problem. It's the most important problem in forward kinematics, because in this type of mechanisms, forward kinematics are difficult. This is a classic example of a parallel robot. In parallel robots, forward kinematics are difficult. Inverse kinematics are easy. Inverse kinematics here would be, given the position of the end effector, let's compute the length of the legs. So this is trivial. But the forward kinematics is very hard. There are 40 solutions, and they can all be real. And it took a few papers to prove the cardinality, the degree of the variety. It's a zero-dimensional variety and has degree 40. In the middle, I have the picture that I started with. It is a famous experiment these days to use NMR in order to compute the 3D structure of biological molecules. And this is very important, as you realize, because we learn the geometry of the molecule. The geometry of the molecule determines the chemical behavior of a molecule, the connections it is going to do in the blood, the drugs that can be applied to this molecule. How do we solve the problem of computing the structure? NMR gives us the distances between the atoms. So you can think of having points in 3D space. We know some of the distances precisely. Some distances are very approximate, and we try to compute the coordinates. So this is a very standard mathematical problem, and it was a breakthrough in chemistry and biology. It led to the chemistry Nobel about 20 years ago for Woodridge, who works at in Zurich at ETH. So let me start immediately with the algebraic tools we're going to use, because after all, this is our contribution to the field. So we are going to focus today on systems that have some structure. They are well constrained, so they have the same number of variables and polynomials. I denote variables and polynomials by m, for reasons that will become apparent later. And I would like to focus on systems that have some kind of structure. So multi-homogeneous structure is not a lot of information. It's not a completely general system, of course, but we could also try to apply, for instance, sparse elimination theory, Newton polytopes. So today I'm not going to talk about Newton polytopes. I've talked many times about Newton polytopes, and I like the area, but today I'm going to use this intermediate kind of structure. So we're going to consider the vector of all m variables, x, and we're going to partition the variables into subsets. So in this example, n is the number of subsets. You see that the notation may be a bit strange for algebraists, but it connects to the graph theory problem I have behind. So I will have n groups of variables. Every group or subset of variable contains di variables. So x11 up to x1 d1. So these are the variables in the first subset, and different variables in the other subset. So it's a partition. The cardinality of the set, as I said, is denoted by di. Capital Xi is the subset. N is the number of subsets or groups. And of course, the cardinalities must add up to m. I underline the fact that these are affine variables. So when we're going to consider the systems in their multi-homogeneous structure, we're going to require that the polynomials are homogeneous in every subset. And how do we do that? We are allowed to add a homogenizing variable in every subset. So typically this is denoted by x1, 0 up to xn 0. Here I only show you the affine variables, okay? To impose a multi-homogeneous structure, I'm allowed to add n homogenizing variables, 1 per subset, okay? So I require that every polynomial pi be homogeneous in every subset capital X, J. And now the degree of the polynomial is, of course, determined by the degree that the polynomial has in every subset. And since we have n subsets, I need a vector of integers to denote the degree of every polynomial in every subset. Okay. Then we say that the polynomial system is of type d1 up to dn. Again, these are the cardinalities. And delta 1 to delta m, these are the vectors of degrees for every polynomial equation. And since we have n equations, these deltas are vectors of this type. Okay, they tell us what is the degree of each polynomial in every subset. So you see the structure must be such that every polynomial obeys the same partition of variables, but it can have very different degrees in every subset of variables. Okay. Now, the last sentence is important. I would like to emphasize the fact that what is sparse? Sparse means that not all terms have non-zero coefficient. Okay, so yeah, I only require that the maximum degree is delta ij for polynomial I and variable set j, but there would be missing terms. Okay, and in fact, you'll see that our equations are very sparse. Very few terms will be there with non-zero coefficient. But today, I'm not taking advantage of the missing terms. I'm going to use the structure of the multi-homogeneous system. Okay. So it will be an open question if we can do better than what today's results tell us by exploiting the sparseness, the missing terms. Today, I'm only going to use the fact that the variables can be split into subsets and every polynomial be multi-homogeneous in these subsets. Okay, so if we have a polynomial system like the one I just described, there is a famous extension of Bézout's theorem that goes by the name of multi-homogeneous Bézout, and the abbreviation is m-Bézout, that gives us a bound on the number of roots, which is better than Bézout's bound when the system was multi-homogeneous of that type. To tell you the truth, Bézout's bound counts projective roots. The multi-homogeneous Bézout bound counts roots in a product of projective spaces that I show here in the middle of my slide. So it's not exactly the same count. For applications where we only care about affine roots, this is enough, and as I said, is tighter than the Bézout bound of the same polynomial system. And most of the time, the multi-homogeneous Bézout number equals the mixed volume of the system. So I know very few examples, although I work in this area every day, I know very few examples where the mixed volume is smaller than the multi-homogeneous Bézout bound, which tells us that even with this kind of structure, we can have a pretty good bound on the number of roots. Of course, with Newton polytopes, which is a stronger structure, we may get a tighter bound, but in most cases, we don't get tighter bounds. We have to find very special systems where mixed volume is smaller than m-Bézout. So let's see what is m-Bézout and how easy it is to compute it. So the multi-homogeneous Bézout bound tells us that if I'm given the multi-homogeneous system, then I define a new expression, which is the product of linear forms. What are these linear forms? They are defined by these symbolic variables capital Y with coefficients that are the degrees delta. Delta, I recall, are the degrees of every polynomial in every subset. So I create these linear forms. I take the product of these linear forms. There is one such linear form per polynomial. And I take the product because m is the number of polynomials. And then in this polynomial with respect to the y's, I consider the term which is the product of the y's to the power that corresponds to the cardinality of the variable subsets. So the T1, Tn is the cardinality of the variable subsets. I take this nice monomial, its coefficient is the m-Bézout bound. Okay, the coefficient of this monomial is an upper bound on the number of roots in the product of projective spaces. And if the original system had sufficiently generic coefficients, This bound is tight. Otherwise, we shall have roots at infinity. Okay. The bound is tight. It means that this is the number of affine roots. Otherwise, some of the roots are in projective infinity. So in this example, I have polynomials in two variables, and I decide to consider this system as multi-homogeneous in variable subsets capital X1, capital X2 that are unitary subsets. So you see that the degree is 2 in the first polynomial for X1 and 1 for all the other degrees in both polynomials. So I consider these linear forms. The first linear form corresponds to F. The second linear form corresponds to G, because G is multilinear. That's how I consider it. It's a sparse multilinear system with a constant term. Okay. I mean, I think it's obvious how this is a multi-homogeneous system, right? It's sparse, some terms are missing, and this term can be made multi-homogeneous by multiplying by the homogenizing variable in every subset of variables. So I consider this set of linear forms, I expand it, and I consider the monomial y1, y2, the coefficient is 3, and this is a bound on the number of roots. Okay. How easy is it to compute the m-Bézout number in general? So this is a toy example. I would like to apply this to larger systems. In practice today, we can solve systems with 20 polynomials maybe and 20 variables. If they are sparse and of low degree, we can go much higher. So we would like to be able to do that for, let's say, 50 polynomials and 50 variables or more. It turns out that the computation of m-Bézout bound is equivalent to a permanent computation. If I construct the matrix of the multi-degrees, recall that this is not going to be a square matrix if I just take the deltas. So I take the deltas and I repeat them a sufficient number of times, actually as many times as there are variables in the subset. And I end up with a square matrix. It's permanent, gives me the multi-homogeneous Bézout bound. And we know that permanent is a very hard problem. It's the central problem in the complexity class Sharpie-hard. Sharpie-hard is the equivalent of NP-hard complexity problems when the question has an arithmetic answer, because NP-hardness concerns problems that are decision problems. The answer is yes or no. Is there a clique of size k in my graph? Or is there a route for the traveling salesman problem with cost k? Here the question is, what is the value of the permanent? And these problems are called Sharpie. Sharpie-hard means that these are hard problems. There are some very interesting results that gives us bounds on the permanent by a closed form formula. And the most famous bound were derived independently, but following similar techniques by Bregman and by Mink back in the 60s and 70s. Okay, so because this answers the question, how can I avoid a very tough computation? Because Sharpie-hard means it's an exponential cost for this computation. How can I avoid it? One way is to bound the m-Bézout number by Bregman-Mink. Today, I'm going to give you another way to bound the m-Bézout bound for certain classes of multi-homogeneous systems. This is the main result today. We're going to derive tighter bound than Bregman-Mink in closed form, so immediate computation, almost, but they apply to a smaller class of multi-homogeneous systems. Okay. Now, another question that comes up is, when I give you a polynomial system, what kind of multi-homogeneous structure are you going to impose? What is the partition of variables that is best? Okay, so to optimize the partition of variables is another hard problem. And it was proven that we cannot even approximate it optimally. So the optimal partition of variables, the partition of variables that will minimize the m-Bézout number for a given arbitrary polynomial system cannot be approximated in polynomial time. It's not fast approximable, let alone computed exactly, unless, of course, P equals NP. Okay. So we understand that these are very hard problems, and that's why a result that gives a good upper bound, even for a class of multi-homogeneous systems, should be useful. Let's see what are the main contributions today. So I will be given a multi-homogeneous system that has some extra structure. That's why I'm putting the word structure in orange. I'll define the kind of structure, but unfortunately our result does not apply to all multi-homogeneous systems yet. This is a nice open problem. Given the system, the algebraic system, I'm going to define a graph. The graph is simple, it has no loops, and it is undirected, okay? It's a simple undirected graph. Then I'm going to study ways to orient the graph, to impose directions. And I'm going to relate the graph orientations to the multi-homogeneous Bézout bound. I'm going to give a closed form upper bound on the number of graph orientations. So automatically, this gives me an upper bound on m-Bézout for the original multi-homogeneous system. It is better, as I said, than Bregman-Mink for permanence. And it also solves in a nice way some enumerative questions in these distance graphs that come from molecular biology, architecture, and robotics that I mentioned at the beginning. Okay, so let me go a bit faster. So I'll go back to the combinatorial problem. So the combinatorial problem is given a graph like the ones I showed at the very beginning. I would like to find the coordinates of the vertices. So I'm given edge lengths for some of the edges, and I need to find coordinates. In other words, I would like to embed the graph into the Euclidean space. So I would like to associate vertices to points in a Euclidean space of dimension D. D is typically 2 or 3, such that when I measure the distance of the embedded points, of the embedded vertices, this is the distance equals the edge length of the input. So this is my first bullet. It says that embedding is a map that sends vertices to points such that the distance of the embedded vertices, the Euclidean distance, equals the weight lambda of the corresponding edge whenever this edge was given in my initial graph. Because I'm going to apply algebraic geometry, I would like to go from the real space to the complex space. I don't know many results in real algebraic geometry for these problems, and this would also be a nice open question. So I could consider a complex embedding, and then I would consider that the modulus of this difference, this is a complex vector, it would have measure equal to lambda, the weight of the edge, if the edge is given in the original graph. Now, I'm interested in the generic situation, because the generic situation maximizes the number of embeddings. So if I would like to know what is the maximum possible number of embeddings, I can consider generic length for my input graph, and then I'm going to bound the number of embeddings. Now, an important notion, which is useful in practice, is to consider graphs that have a finite number of embeddings. For instance, the triangle down here, if I specify edge lengths, has a unique embedding if I fix the origin, if I fix one graph and I require it to be on the positive y-axis. even if I can flip, even if I can reflect, it will have two embeddings. So modular rotations and translations, the triangle has a finite number of embeddings. That's why it's called rigid. However, the quadrangle, even if I fix a vertex, an edge, and of course all the lengths, it can have an infinite number of embeddings. Okay, it can move like that. So it is not rigid. It is a flexible graph. To make the quadrangle, the parallelogram, let's say, to make the parallelogram rigid, I would need to add a diagonal constraint. I would need to add an edge with specified length that would split the parallelogram into two triangles. And then it would have a finite of embeddings. Okay, a finite number of embeddings for the first triangle, and then the second triangle, again, it has a finite number of embeddings, modular rotations and translations. Okay, so today we're going to focus on rigid graphs. Typically, as I said, generically rigid, because the lengths are not specified in number. Okay, I only know that some edges have specified lengths, but I'm not given the length. Typically, I want to study problems where I know which edges are there, but the actual edge length will come online. It will come later on with the experiment, with the biological experiment, for instance. And another interesting concept is that of minimal rigidity, which says that the triangle, for instance, is minimally rigid because if I remove one edge, it becomes flexible. Okay. In other words, the graph has exactly the number of edges required to make it rigid, but not extra edges. If it has extra edges, usually it will have a single embedding. Okay, this also comes up in applications, but it's not so much, it's not so interesting from a mathematical point of view. Okay. And then there is another recent extension of the whole theory to spherical embeddings, where we require for the points to be embedded on a sphere. So we have some additional constraints that they must all lie within radius from some center. Okay, but today I'm not going to go into spherical embeddings because I don't have the time. So, a very important theory from more than a century ago gives us one direction to characterize rigidity. It says that if the graph is generically rigid and minimally rigid in some dimension d, then the number of edges, the number of constraints, is the number of constraints we would expect as algebraists. Because in algebra, we know the generic number of equations to make a polynomial system well constrained. We know that the constraints should be equal to the number of variables if the coefficients have generic values. That's what Maxwell says, that the number of edges must be, so the number of edges are the constraints essentially, must be equal to the degrees of freedom in a graph. What are the degrees of freedom? What are the unknowns? The unknowns are the unknowns for every vertex, because I have to embed it in a space of dimension d, minus the number of coordinates specified in order to fix the graph and avoid translations and rotations. So if d is 2, this quantity equals 3. It means that I fix the origin, 2 coordinates, and I fix the y coordinate of another vertex to be 0. So I require that the first edge lie on the x-axis, and its length, of course, is given by the constraints here. Okay. I need to fix 3 coordinates equal to 0. In 3 dimensions, this goes up to 6 and so on. Then Maxwell says another, of course, important property, that no subsystem should be over-constrained. So for every subgraph, the number of edges should not be larger than the degrees of freedom within the subgraph. Okay, so very intuitive for algebraic geometers. Okay. However, we have no idea of the opposite direction. We do not know which edge counts will lead to rigidity, except in the plane. In the plane, for d equals 2, there is a theorem that is attributed to Laman. So these are called Laman graphs from 1970, but apparently it was first discovered by a woman that worked in the early 20th century, Paula Geiringer, said that a graph with this number of edges is generically rigid. We have no idea for the converse direction in 3 and more dimensions. Of course, in 3 would be very interesting. There are some partial results. Okay. And I already talked about this combinatorial quantity, which is the number of fixed coordinates to avoid rotations and translations. So the problem that I'm interested in is to count the number of embeddings. I know that it's a finite number, so let's see what is the enumerative problem. I could construct a polynomial system that has approximately this number of variables, d times v, okay? And because these equations are quadratic, I'm going to show you later the polynomial system, but you can imagine these are edge lengths constraints. So I have degree 2 in every equation, so the trivial bound is given by m-Bézout, 2 to the number of equations. Very easy, and surprisingly, it has been the best bound available until last year that we started applying multi-Bézout bounds, okay? Moreover, we know that it's very loose because the best lower bound we have managed to compute is 2.5 approximately to the v, whereas this is 4 to the v. And in 3-dimensional space, about 3 to the v, and the upper bound is 8 to the v. So a large distance between lower and upper bounds. People tried some very heavy-duty algebraic geometry, determinantal varieties. There is a rich theory, of course, from determinantal varieties that was applied to the specific problem by Borsa and Strainu. Mixed volumes were examined by Stevens and Theobald in Stevens' thesis, 2010. None of these approaches improves the Bézout bound asymptotically. The improvements are negligible, okay? However, with multi-homogeneous Bézout bound, we managed to improve the upper bound for dimension 5 and beyond. Of course, in applications, we are mostly interested in dimension 2 and 3, okay? However, this approach gives the way to the method I'm going to describe today. And when applied to graph orientations, it gave us the first non-trivial upper bound, even for dimension equal to, which is 3.77 to the v, better than 4 to the v, still far away from the lower bound, okay? And actually today, I'm going to start from this result and show how it can be used to bound the multi-homogeneous number of a large class of algebraic systems, not necessarily related to graph problems. Before I go on, let's see how useful are the bounds we get. I show you the asymptotics. How about actual numbers? So these are the lower bounds that we have, and these are the upper bounds by Bézout, okay? In 3 dimensions, it's exact for the special case of planar graphs, the graphs that could be drawn in the plane, not embedded in the plane, not having vertices acquire coordinates, but drawn in the plane without edge intersections. Okay, let's see the connection of algebraic systems and graphs, because I talked about graphs right now. Okay, so this is the polynomial system I already mentioned. It's the naive approach. Let's see what happens in 2D. I fix 3 coordinates to be 0, And to avoid scaling, I can fix one length to be 1. Okay, because the number of embeddings doesn't change if I scale the given edge lengths. For the rest of the edges, I say that the Euclidean distance between point xiyi to point xjyj must be equal to the edge length. And because I take the squared length in Euclidean space, I take the square of the edge weight. Similarly in 3D. So you see all of these equations have degree 2. How many are there? About the number of edges, it's exactly, it's the number of edges minus 1 here. Okay, because I fixed one edge length to be equal to 1. Same here, number of edges minus 1. Okay. But we can do better if we try to exploit multi-homogeneous structure. So in this polynomial system, there are 2 tricks. I will start with the first trick, and then the second trick is to impose multi-homogeneous structure. The first trick is to group the squares. So this is a standard trick in algebraic geometry, sparse elimination theory. We used it with Theobald in order to derive smaller mixed volumes. And we achieved smaller mixed volumes. They are in Stevens' thesis. It's a paper by Stevens and Theobald. We achieved smaller mixed volume, but again, we do not improve the asymptotic bounds. So what does this say? It says I introduce a new variable for every vertex that is equal to the sum of squares of the coordinates of this vertex. So when I come to the standard equation that it says length of the embedded points equals length of the edge squared, here I should have, you see, if I develop this equation, I have the sum of squares, and then I have bilinear terms. Here I have the sum of squares in these new variables, and here I have the bilinear term written as an inner product of the capital XU vector times the capital XV vector. Okay, so these are the bilinear terms that come from raising the parentheses to the squared. And it's important to replace squares by new variables because in the context of sparse elimination theory, this removes roots at toric infinity because there will be some roots at infinity, but in this formulation, if all of the coordinates are 0, this should be 0, S should be 0. But toric elimination theory does not allow for all the coordinates to be 0, okay, of a solution. So mixed volume is not going to count certain solutions in toric infinity. Okay. So this is a trick that applies when one wants to minimize mixed volume. It's not very relevant today, but we are using this formulation because it gives us a multilinear system now, actually a multilinear subsystem, and then a subsystem which is quadratic. But when I go to the m-Bézout theory, you recall that the bound is going to be the coefficient in the development of this expression. Remember, it's a product of linear forms that correspond to the equations. The linear form that corresponds to these equations have this linear form. It's 2yi, yes, because there is a partition of variables contains, the subset of variables contains the coordinates and the new variable s, okay? And this equation has only this group of variables and the constant. It's quadratic in this group of variables, hence the term 2yi, okay? So this is the product of these, corresponds to these equations, and then the multilinear equations, the bilinear equations, gives us a product of these forms. But the first product is easy to handle. I take out 2 times the product of the y's, and I keep the product of these linear forms, which are very simple. And then I'm looking at the coefficient of this term, multiplied by the product of 2 to the n minus d. Now recall here, n is the number of vertices, so is the number of variable sets, and d is the space, is the dimension of the space, which equals to the number of coordinates when I embed the vertex. That's why I'm using n and d in this way, which is strange for algebraists, but it comes from the graph theory, okay? N is the number of vertices in the graph, and d is the embedding dimension. So now the problem becomes to study the development of this product. I have taken care of this part. It gives me a power of 2. And now it suffices to bound this product. So I would like to estimate, to bound the coefficient of this term from this product. So I can focus in the product of linear terms, and these are linear terms with only 2 non-zero monomials, okay? Sorry, linear forms with only 2 non-zero terms. And now the first observation is that the coefficient I'm looking for in this product of linear forms with 2 terms has a combinatorial meaning. Because what does it mean to expand this expression and look for this coefficient is to use yi for every edge, for every pair, to use only one of the 2 y's, and to use yi, some yi, exactly 2 times in order to build this power. Okay, so there's a combinatorial meaning. It says use one of the 2 every time, and a total of 2 times of them. Okay, so if I consider the graph from where I got this expression, this says that for every vertex, I need to choose, I need to consider the edges from each vertex, and I need to pick d of them. So picking d of them for every vertex, I need to pick d. When I pick d, it means that I orient them so that I don't pick the corresponding variable at the other end of the edge. The fact that I have to pick one of the 2 y's means that for every edge in my original graph, if I pick one endpoint, I should not pick the other endpoint. So this is like orienting the graph. If I choose one orientation, I cannot choose the other orientation. So orientation, we should think of orienting a graph as giving the preference in one endpoint rather than the other endpoint. Okay, so choosing one endpoint, choosing one vertex per edge. This is what I say here. Choose one yi per edge. This is equivalent to orienting in both directions on the undirected edges. So I need to impose directions. So I need to choose an orientation such that for every vertex, the out degree is d. So I choose the vertex d times, okay? And I can ignore vertices that are fixed, like the origin and the first coordinate. So these are the fixed vertices. So there are 2 fixed vertices in the planar problem. So when d is 2, I fix a clique of size 2. A clique is an edge. When I go to 3D space, the clique is a triangle. So I fix the triangle to avoid rotations, translations. Okay. So vertices in the clique are not important. So they have out degree 0. So only in degree. So I cannot choose them. And among the other vertices, I have to choose them exactly d times, not more, not less. So computing this coefficient becomes a graph theoretic problem. Count the ways to orient the graph such that these constraints are satisfied. I'm going to call them constrained orientations or valid orientations. Okay. So that was the crucial observation, I guess. The corollary is that if I count the number of orientations, I have a bound on the number of embeddings. Okay, this is obvious because orientations gives me m-Bézout. M-Bézout bounds the roots of the algebraic system, which expresses embeddings. So how many are the embeddings? I have this power of 2 times b, which is the number of orientations. Okay, so far so good. And then the rest of my talk is going to consider bounding the orientations and connecting them to algebraic systems that are more general than the systems we had from the graphs. This is an example. So I start with a graph, which is very famous because it's rather small and rigid, and it's hard to count the number of embeddings. It goes by the Zark or the double. It has many names. Yeah, it's like a prism. So if you think about it, it's the graph of a 3D object, which is a triangular prism. But now I can fit it in the plane. It has 6 vertices, and it's the first non-trivial example, because with 5 vertices, things are easy. Or with 3 vertices, we have the triangle, which is very easy. So I would like to embed it in the plane, and the click is the dashed edge, okay? I can choose any edge, and this is an open question. It's an open question. What is the best click to choose to minimize the upper bound I'm going to compute? I don't have a good answer for that, so I choose any edge to fix it. Now, if I do it by hand, because I have not given you ways to count orientations yet, if I do it by hand, I see there are 2 orientations that are constrained. So for every vertex, the out degree is 2. For this vertex, the out degree is 2. For this, and here is the same. For this vertex, the out degree is 2. Okay, what are the colors? The colors show you in degree. So it would originally, actually, when we made that figure, we were imposing the equivalent constraint, which was for the in degree to be 2. So you see this vertex has in degree 2, red. Maybe not, no, I'm sorry. Okay, sorry, the red constraint shows a vertex that belongs to a vertex that is fixed. So it must have out degree 0, okay? The rest of the edges are green and are oriented by choice, okay? Sorry, it's not what I said. It's that the red ones must necessarily be oriented that way because the fixed vertices should have no outgoing edge. And then I have a choice on this cycle to make it green or blue that gives me the 2 orientations. So the 2 orientations lead to an upper bound, which is 32. And interestingly, this is also the mixed volume of the corresponding system. The actual number of complex and real embeddings is 24. It's not easy to prove. You cannot get it by a standard bound like m-Bézout or mixed volume. One has to look very carefully and count solutions. And it was done in the 80s for the first time. Okay, so this is a very interesting algebraic problem because the actual bounds we have are loose and it's a rather small system. Let me give you a couple of hints about the proof before I go to the applications in algebraic geometry. The proof starts with the original graph and then eliminates vertices in order to get to smaller graphs. Every time it eliminates a vertex, it counts the number of orientations that correspond to that vertex. And then it takes the product of all these possible orientations. The elimination process maybe is similar to a variable elimination process. That's one of my favorite open questions. the thing is that if you start eliminating vertices, although we start with a simple graph, which is connected, of course, at some point we get to a pseudograph. The pseudograph is what we get when we eliminate a vertex, but we do not eliminate all of its incident edges. Okay, when I eliminate a vertex, I keep the edges that are incident to that vertex if they are incident to another vertex that remains in the graph. But of course, I have to orient them towards the deleted vertex, because the deleted vertex is like a fixed vertex. It's like fixing more vertices than the original click K. Okay, so it's a process of fixing vertices. So I end up with some normal edges in white, but I also have these red, pink hanging edges. So for every vertex, it has the normal degree, but it also has the hanging degree, the number of necessarily outgoing hanging edges. The sum of normal and hanging degree is the total degree, okay? So every vertex is characterized by the total degree and the hanging degree equivalently. Their difference is the normal degree. So this is an example where we fix the dashed edge, and then what we do, we remove it. And then when we remove these vertices, we end up with hanging edges that point to the fixed vertices. So this is the definition of the first pseudograph in my elimination process. Okay, these are so they point downwards, they could be pointing upwards, okay? This is what we get after removing the fixed edge, okay? And the technical lemma says that the number of orientations that I need to count, the valid orientations, are obtained here by counting the number of orientations in this pseudograph. Then I have to multiply that with the number of orientations in the next step. So I have a product of number of orientations that gives me the total number of valid orientations at the end. Okay. And this is going to be an upper bound on m-Bézout. So this tells you the entire process. I start with vertices and I start deleting edges, and the number of orientations that I get at every step, we call it value or cost in the paper. So the product of values is the number I need at the end, B. When I end up eliminating and I get a tree, then it has only 1 or 0 orientations. So, of course, I do not multiply this case, right? Because I don't want to multiply with a 0 nor with 1. I multiply the other thing. That's the stopping criteria. That's the base of the recursion. Okay, and there are two kinds of elimination. Either I eliminate a single vertex, or I eliminate a path of vertices that I show you here. This is an example of eliminating a vertex that has 3 normal edges and 0 hanging edges, and the resulting pseudograph has 3 orientations. So the value here is 3. That's the value of that step that I need to multiply with the other values. Okay. I could eliminate a vertex with total degree 3, but 1 hanging edge, and then I see there are 2 possible pseudographs. So 2 possible orientations of the result. Okay, so the value is 2. And for accelerating this elimination, I can eliminate vertices on a path if they are all extended degree 3,1. And this kind of elimination always has 2 resulting orientations, so the value is always 2 here. Okay, I don't need any fancy calculation for that. An important result that we got very recently, so this is not published yet, we got it last year, it's on arXiv, and we have submitted the paper, is to bound a priori in a closed formula. That means the number of orientations. This is our new result. It's very combinatorial, and we get these fancy expressions. To make life simpler, I can tell you that beta is always less than 1. So to bound this alpha to the nth power times beta to t minus 1 is the number of hanging edges. One can ignore the beta term because it only helps me. But to simplify calculation, I could only maximize this parenthesis and get alpha to the n. Okay, and this is much better than Bézout's bound. This is the example. So for dimensions that are interesting, but also for larger dimension, the Bézout bound for the graph embeddings is 4 to the n. Okay, so here I show you the basis raised to n in order to get the embedding number, the bound on embedding number. So the Bézout bound is 4 to the n, or 8 to the n, as already discussed, for space. Our older paper, as I said, improved only dimension 5 and beyond. The new result says that alpha to the nth power is approximately, so this is a simplification of the formula before. I should say here asymptotically, because I'm ignoring some lower order terms. And asymptotically is 2 alpha to the n. And we see that the bound that we get is of this order. So it's better than Bézout even for the planar case. Okay, this is the result I announced at the beginning, and that's how it improves the state of the art even for larger dimensions. It's joined with Raimundas Vidūnas from Lithuania, Vilnius. So I will conclude with a couple of slides for extending to a larger class of multi-homogeneous systems. So our theory applies to all kinds of multi-homogeneous systems, actually to polynomial systems that can be put in this framework. Every polynomial contains 2 variable subsets. So I need to define a partition of variables, and then I check that every polynomial has 2 subsets of variables, and they are different. So I don't want polynomials containing the same pair of variable sets. This corresponds to edges in the original modeling, okay? Moreover, another constraint is that the degree of every polynomial is the same in both variable sets. So these are the bad news. These are the constraints, and they come from the original formulation. Hopefully, we are working right now on removing some of these constraints. Okay. Okay. However, the degree can be different. It does not have to be 2 or 1 like before. The degree can be arbitrary in these polynomials. Okay. This is an advantage. This is how we enlarge the class of systems studied so far. Okay. Then we get a graph that is simpler and connected, like before, where vertices correspond to subsets and polynomials to edges. An obvious idea we are considering is to consider super edges. Okay, this is a standard tool in graph theory, to consider that edges are subsets of variables, not only pairs of variables. Okay, and then with this setup, if the polynomial system obeys these rules, then we apply the results that I showed you before. So we have a closed form bound for m-Bézout, which comes from this Greek alpha. Okay, this is the result. This is what I just said. So if the polynomial system obeys these constraints and it has m equations and m unknowns, the degree of the polynomials can be arbitrary, but it must be the same in both variable subsets. Then the m-Bézout number, given by the number of orientations, times the product of the degrees. This used to be 2 in the original formulation. Now it can be arbitrary delta, product of arbitrary deltas. But one has to count the orientations, and this is where we can bound capital B by the closed form formula that uses alpha to the power of n. So we have a fast way to bound m-Bézout without going to the permanent. Okay. So if I bound the number of orientations by alpha to the nth times beta to k minus 1, I have the best upper bound available right now. This is better than the bound on permanence by Bregman-Mink if the polynomial system satisfies my constraints above. Okay. This is an example. One is given these equations. We observe that they can be modeled into two subsets in every polynomial. These are in total 5 subsets of variables. So it's a difficult problem to find them, but one can do it in many ways. It's hard to find the optimal partition, but any partition will give some bound. The degrees are 1 and 2, more general than the graph problem before. And when I apply my theory, I have to count the orientations. They are 6. Okay, 6 orientations. Okay. I should not say so. My bound is going to be 13. Yeah, this is my last slide. Thanks. The m-Bézout is 6, so my bound is not tight. However, it's much better than what we had before. Okay. The open questions I already mentioned. The bibliography is available in the proceedings. Thank you very much for your attention. Sorry for going over time.
Thank you very much for the very nice presentation. So, are there short questions or comments? Yeah.
Emiris, does there exist the concept of, so to say, universal, minimally rigid graph? What I mean is that a graph that is minimally rigid, no matter what the dimension is. So, for example, just a triangle seems to have this property, just like this Desargues configuration. However, a junction of two triangles is, as far as I can see, minimally rigid in the plane, but not in the space. So does there exist such a concept, independent of dimension?
So that's an interesting question, because usually people fix the dimension in what I have seen. What I know is that there are some determinantal conditions to define what is the minimum dimension of embedding. But I have not seen the universality concept that you are suggesting, Timur. So not in the way that you are proposing. Cayley and Menger have conditions that tell us what is the minimum dimension of embedding, but not the universality that goes across dimensions. That's a very good question, actually.
Okay, thank you very much, Ioannis.
Okay, other questions?
My question is, when you compare m-Bézout bound with mixed volume bound due to Bernstein-Khovansky-Kushnirenko, if I'm right, you don't take into account multi-homogeneous structure. Yes?
Correct.
Okay, thank you. But,
it's two different things.
Okay. But maybe there exists some possibility to improve mixed volume bound for this partial case for mixed.
Yes. People tried, but it's possible. The two bounds are very much related. But you're right. We have not exploited, in fact, sparseness at all in this approach.
Okay.
So maybe BKK would be the correct way to go. Probably.
So
yeah, thanks.
If there are no further questions, so let's thank the speaker again.
Thank you.
And it's time to proceed to the next speaker. So please stop your, yeah, okay. So is Dima Grigoriev here?
Yes, yes, I'm here. Okay, do you allow me to share the screen?
Yeah.
Okay.
I think there is, it's possible.
Nothing happens. Okay. Do you see my slides?
Not yet. Yeah.
Do you see my?
Now we see.
We see the screen and yes, the slide.
Okay.
Okay. Okay. Fine.
So it's a pleasure to introduce the next speaker, Dima Grigoriev from University of Lille, and who will speak about entropy of the radical of a tropical curve. Please.
Okay. Thank you. So actually, this is one of the steps to my old plan to prove the existence of some version of tropical Hilbert polynomial. So first I start with some basic concepts to remind about tropical algebra. So the basic object of the tropical algebra is a tropical semi-ring. Tropical semi-ring is a semi-ring. It's an idempotent semi-ring endowed with two operations, which I will denote like this. So the main source of the tropical semi-ring is usually ordered semi-group, and then this order T, say the order semi-group T, is a tropical semi-ring with inherited two operations, where the addition is the minimum and the multiplication is the group is the semi-group operation. And if you have some additional structure on this semi-group, say it is abelian group rather than a semi-group, then T is a tropical, is called tropical semi-skew field in case of the ordered group. And if it is more of abelian, then you can talk about tropical semi-field, where the tropical division is placed the role of the subtraction. Few examples, typical examples of tropical semi-rings. First example is the non-negative integers, or the non-negative integers with the added infinity. They are commutative tropical semi-rings. And infinity plays the role of a neutral element. One can easily check the axioms of neutral element. And in its turn, the zero plays a role of the unity. If you consider not just the non-negative integers, but rather all the integers, or all the integers with the added infinity, you get a semi-field, because now you have a subtraction. So as we talked, it is the tropical division. And an example, say, of the non-commutative tropical semi-ring is the tropical semi-ring of n by n matrices over some semi-rings, say over Z with infinity, with the usual rule for multiplication of tropical matrices. So it was about tropical semi-ring, and another important object is a tropical polynomial. So to define tropical polynomial, we start with a tropical monomial. So just take a variable and its tropical product, say I times, and monomial is the tropical product of these powers of variables multiplied by some coefficient A. And one can talk about its tropical degree, which is the sum in the usual sense, similar to the classical sense, as the sum of the powers. And classically, one can view tropical monomial as a linear function with the integer coefficients. Say the free coefficient can be, say, real, and the coefficients at variables are integers. So we have defined monomial, and the polynomial, similar to the classical case, we define as the tropical sum of the monomials, which classically it is nothing else but the minimum of linear functions. So tropical polynomial can be viewed as a minimal of linear functions, so a convex piecewise function. And well, this is very similar to classical stuff, but what differs essentially tropical from the classical world is the concept of the tropical zero. Tropical zero is a point of, say, of the polynomial, tropical polynomial f, at which the minimum is attained at least two times. So for two different values of j, for two different monomials. Geometrically, one can view this in the following way. So we discussed that the tropical polynomial is the it is the minimum of linear polynomials. So the tropical zero is a point where this function is not differentiable. So when at least two linear functions have the same value. Okay, and the tropical variety is again similar to classical stuff. We want to define the set of the points of zeros of a polynomial, and this is so we say have a family of tropical polynomials of 1 of k in n variables, and the tropical variety we define simply as the set of the tropical zeros of all these polynomials. Geometrically, tropical variety is a finite union of polyhedra. So this hydra means that they can be unbounded. And well, we denote also the tropical variety as the zeros of a. Also, one can view this as the zeros of the semi-ring ideal I of 1 of k, so generated by f1 of k. And another important thing is that we need to define the similar to the classical case, it's shift is a just the multiplication by a monomial, as you can see from this formula, and it's again an element of the tropical ideal generated by a polynomial, by a tropical polynomial. So we need also the concept which is standard in the commutative algebra. We need what we call the linearization. So what we do now, we replace the monomials by new variables. This is a standard thing which is done in commutative algebra. So if in the commutative algebra an ideal of polynomials, we view it as a subspace in the space of polynomials with the basis of monomials. And then we define linearization as this as an element of this subspace of this monomial. We truncate, say, by n capital the degree of these monomials, and in this now finite dimensional space we consider the truncated ideal. And linearizations appear as say as the roles of the Macaulay matrix of polynomial f. Okay, and so we consider the linearizations, and now we consider a point from the tropical prevariety, so the point satisfying polynomial f, and then we consider the point where the values of the variables, so u, I remind that u of indices are the variables, so the coefficient which appears at the coordinate k1 kn is just a linear function in this at this point with k1 fk, and this is one can easily see that it's a tropical zero of any linearization. So the idea of linearization is just to view the polynomials as as I say, in classical world, as the elements of the linear space of infinite dimensional linear space of all the polynomials, and we are looking for their tropical zeros, and these are the tropical zeros of these polynomials. We would like to consider, as I said at the beginning, some analogy of the Hilbert's polynomial. And in classical world, we say, well, what we do, we take the space of all the polynomials as a linear space, and a quotient space with respect to the ideal, and then we take the dimensions of the truncated its components with the filtration of by the degree. But unfortunately, this is does not work in the tropical setting, because in the tropical setting there is no reasonable concept of the quotient space. So we would like replace it by the asymptotics of the behavior of the dimensions of these of the dimensions of these components. Okay, so we denote by U capital N the tropical prevariety of all the points being tropical zeros of all the linearizations. Then we claim that there exists, so the dimensions of this, they just play the role of the values of Hilbert function. So the dimensions of this quotient components of the quotient space. But unfortunately, as we don't have the quotient space, we replace them by the tropical prevariety. In the classical world, these things coincide, because if we consider the quotient space of the ideal, then the dimension of this quotient space coincides with the dimension of the solutions of the linear systems of the ideal. And this is nothing else but the UN which we considered here. So this limit gives the asymptotics of the components. And we call it tropical entropy. Clearly, this is a real number between 0 and 1. First of all, why this limit does exist? If n small, so we can see the one dimension would be equal to 1, then the function of the dimension would be subadditive. And then the limit exists due to the subadditivity lemma, which is a key lemma in the ergodic theory in the definition of the entropy. And the generalization of this subadditivity lemma also works in the multidimensional case, but then one should be more careful. One should replace the subadditivity by some geometrical notion of the partitions of the, say, of the parallelepipeds and things like that. Anyway, this limit does exist, and we call it the tropical entropy. And so the tropical entropy shows you the asymptotics of the Hilbert function, of the values of Hilbert function. In the classical commutative algebra, we know that Hilbert function behaves as a polynomial, and starting with some points, so for sufficiently big values. But here we don't know it yet, but at least we are looking at the asymptotics behavior. And clearly, so far we defined it, the entropy for the single polynomial, but one can literally generalize it to semi-ring ideals. And what is the relation to Hilbert polynomial? So the tropical prevariety plays a role similar to the quotient ring with respect to the degree filtration. Therefore, the entropy plays a role of the coefficient at the nth power of Hilbert polynomial of say, a polynomial G, whatever. But as we know in the classical commutative algebra, this coefficient is always 0. Trivial reasons, because the degree of Hilbert polynomial equals n-1, and for the ideal it equals to the codimension of the ideal. So this coefficient, so this analogy, the same magnitude of to the tropical entropy would be always 0, would vanish in the classical setting. But it is not the case in the tropical setting. It can be positive, and we'll see an example of that. But still, as we don't know much about an analogy of Hilbert polynomial in a tropical setting, we would like to understand at least when entropy vanishes, because vanishing of the entropy is what happens in the classical, always happens in the classical setting. And now a radical of the tropical prevariety. Well, we define the radical just as a semi-ring of semi-ring ideal of all the tropical polynomials for which points are 0. So on which, in other words, the polynomials vanish. Usually in the classical commutative algebra, the definition of the radical is different. Take an ideal, and then we take all the we'll extract all the roots from the values of this ideal. This definition in the classical world is due to the Hilbert's strong Nullstellen Satz, which describes the radical. So that means that this Hilbert strong Nullstellen Satz says you that if you take all the polynomials vanishing on a variety, then it's the same as the radical in this sense. But in this relation, the set of the polynomials which vanish on the prevariety is primary, and then the secondary is the description of the radical as all the set of all the roots of the elements of the ideal. And so we are mainly interested in this radical in this sense. So we take all the elements vanishing on the tropical prevariety V. So we could start just with an ideal, and then we could consider its prevariety of the roots, and then take the radical. So that's another dual way. Okay, and the principal conjecture which I want now to formulate is the following: that okay, we don't know yet what is the structure of the Hilbert function, whether it is polynomial or not. We'll know something. We now know the answer in the one-dimensional case for a single variable. I will say a few words later, but at least we would like to say that if we now take the radical of the ideal, then its entropy vanishes. That's what happens in also in the classical world. So, in other words, if we would know, which is not possibly true, that the Hilbert function is actually a polynomial, then this polynomial would have the correct degree less than n. At least we would know, provided the conjecture would be true. I don't know, it's indeed a conjecture, and my feeling is that it's quite deep conjecture, but at least I know the proof of this conjecture at least in two particular cases. First of all, if V, the tropical variety, which we started with, consists of a finite number of points, then the conjecture is true. In particular, this justifies this conjecture in case of a single variable. So for n small equals to 1, if we consider polynomials in a single variable. And moreover, in this case, we could say something also in the converse direction. So that if we consider tropical univariate polynomial, then the converse is true as well. Namely, if the entropy vanishes, then the multiplicity of each tropical zero equals 1. So in some sense, there are no multiple tropical zeros. And actually, in one variable, we know the answer. What is the structure of the function? Well, I would like to say that it's a polynomial, and in this case, it could be a polynomial of degree 1, so a linear function. And in this case, the leading coefficient would be the entropy. Unfortunately, this is not true, but almost true. This is not a linear function, but it's a quasi-linear function. So this is a sum of the linear function, and indeed with the leading coefficient coinciding with the entropy, and then plus some periodic function, and that's what I call the quasi-linear function. But in many variables, I have no idea about the structure of the. Yeah, this is true as in the classical case. This is true for sufficiently big values, and but for many variables, for more than one variable, I don't know. I have no idea what is the structure of the Hilbert function. And the second particular case is the case of the tropical homogeneous tropical curve. So if we plane curve, so if we consider a single polynomial, homogeneous single tropical polynomial in two variables. So it gives you its tropical prevariety is a tropical curve. Actually, for in homogeneous case, it's quite simple. It consists of a single vertex and several rays emanating from it. And then the conjecture is true, so the entropy vanishes. Unfortunately, I don't know anything beyond this theorem about the conjecture, in particular, say, for the general tropical curve, not homogeneous, so whatever, and so more in the multidimensional case. Okay, and I finish with the example which shows that the entropy could be positive. The entropy could be positive, so for not a radical ideal. So we consider a single polynomial. By the way, it's another difference from the classical setting is that you consider a principal ideal, so the ideal generated by a single polynomial. And from this polynomial you cannot extract the root, but still it doesn't coincide with its radical, and its entropy is I don't know, by the way, the answer. I would think that I believe that here is equality, so that the entropy equals to 0, but I don't know. I know only the lower bound for it, for the principal ideal, by the way, there is no good. I think in this language there is no good analogy of Hilbert's Strong-Nullstellen Satz. So the good description of the radical. Well, there is some very clumsy description of the radical, but unfortunately it's really very clumsy and intricate, and it definitely doesn't coincide with the radical in the classical sense. So you see it already in this example. So for the radical for this polynomial doesn't coincide. Radical in the classical sense would coincide with itself. And so you see that it's really this condition that you consider the radical of the ideal, but rather the arbitrary ideal. It's necessary to vanishing of the entropy. Okay, so thank you for your attention.
Thank you very much. Let's thank the speaker. So, are there some questions or comments?
Is it possible to compute the entropy of the radical of a hyperplane, of a tropical hyperplane in a given dimension, not necessarily two?
Well, look, this is even in this simplest case, which is indeed what you're asking. It's a tropical hyperplane, so given for a single polynomial. I don't know the answer. Well, I believe that it's exactly 1/2, but I know only the lower bound, as I say. It's difficult because look, it's a limit. You need to consider. You need to compute or at least estimate the dimension of the components with respect to the filtration, degree filtration. And then you need to compute the dimension of the space of solutions of the tropical linear systems with growing size, and this is computationally is quite difficult. Actually, the students in St. Petersburg tried to compute for some examples, but they are able to compute for the very small dimensions because it's a quite complicated tropical linear system.
I see.
There is another question.
And you deal with prevariaties, but don't use the tropical basis. My question is if there exists any possibility to simplify computation of entropy using tropical basis, if you know it.
Well, well, look, for no, this would not help much for the computing the entropy, just because you need to compute the solutions of the dimensions of the. So actually, any what I would say the following: that any basis, not necessarily tropical, would be sufficient to compute the dimension of the components. So you don't need the tropical basis. Tropical basis is too complex thing for that. It's much simpler, because it's just a linear system for any basis.
Okay, maybe.
But maybe your question is about the radical. Then it's another story. Then it's much more complicated. And but another thing is that tropical. Well, look, tropical basis does not help to compute the radical. That's maybe the question which you had in mind. But for computing that entropy, any basis would be enough.
Actually, the source of my question is that in some cases you don't need if some monomial exists in ideal, and in this if you compute the tropical basis, you deal with tropical variety, but not initial prevariety. But
well, maybe you're right that it would simplify the computations, but you know, as you know well, the computing the tropical basis is much more complicated than the whole story. But if you already have it, yeah, perhaps it would simplify some computations. I don't know, but well, you know, but for me more interesting is that computing the radical, and for computing the radical in this sense, and for computing the radical tropical basis doesn't help, unfortunately.
So maybe there is a question from Zoomas. So if not, then let's thank the speaker again. And proceed to the last talk. Okay, so are you ready? Yeah. Yeah. So the last talk will be given by Yang Liu. So it will be about linearizability property of Lie symmetry algebra.
Yeah. Okay. Hello, everyone, and this is Yang Liu from KAUST. Today our topic would be the linearizability property of the Lie symmetry algebra. So before we start, I want to say that this presentation is in memory of Vladimir, who's passed away in January of 2021, which is a big loss of us. Okay, so we're gonna discuss about the exact linearization of the ODE. Like typically in applied mathematics, the linearization just means the approximation of some function by its linear part in Taylor series. But here in this presentation, it means completely different. So the meaning of exact linearization, it means like once we have a ODE in like in the form like this, which is explicit in the highest order term, and we want to know if this equation 1 is linearizable through some transformation, and just like a change of variables to make it like to a linear one, like the following. Okay, so we need to notice that okay, in the following of in the rest of our presentation, this equation 1 is the only one which is labeled. Okay, so here is a very simple example. Now we have, firstly we have the nonlinear ODE. And after we made some change of variables, like we call it point transformation. Like here, like t equals to the square root of x and u equals to y. So we can transform this nonlinear ODE to the trivial case, like u prime 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 equals to 0. So we studied this linearizability by something called one-parameter symmetry group. So now let's say we have a point transformation, the old variables x, y to the new variables t and u, and the transformation is the t alpha. Here alpha is the parameter, like so it's kind of like we have a family of transformations. So if we compute the derivative respect to alpha and set alpha equals to 0, we have like two coordinates, like the xi and eta. These two coordinates are expressed in x and y only. So actually the set of these two coordinates, eta and xi and eta, forms a Lie algebra, and so which is called the symmetry algebra. So if you take brackets, you have we have the we have like we have some we have this constant, like I say it's a cube which forms a cubic matrix, and these constants are called structure constants. So this is some basic property for Lie algebras. Okay, so our algorithm is based on this mean theorem, which claims that the equation 1, when like is the order is higher or equal than 2, the equation 1 is linearizable by some point transformation if and only if some the following conditions is fulfilled. So there you can see like there are 3 cases. One n equals 2, and the dimension of its symmetry algebra should be 8. And in this case, this equation 1 is always linearizable to the trivial case. And when the order is higher than 2, like when n is higher than 2, and the dimension equals to n plus 4, we also meet the trivial case. And for the last one, if the dimension is the one of n plus 1 or n plus 2, in this case, the equation 1 is linearizable to an ODE, but this ODE is not trivial. Like they have some non-zero coefficients. And especially for the last case, when the dimension equals to n plus 2, in this special case, we have, it implies this equation 1 can be transformed to a linear ODE with constant coefficient. So, so this special case actually gives us a very interesting algorithm, which I will mention later. Okay, so we already have some very useful packages in Maple 2020, and which can help us to compute a lot of algebraic structures in the Lie algebra, like a derived algebra, and will help us to compute the constant coefficients. But we should know that this algorithm is not working on the Lie algebra directly. Actually, before we said the Xi and eta, they form a Lie algebra, but actually in practice we don't have the explicit form for them. We only have a PD system, and in the system we know that the solution of this system forms a Lie algebra. So all this algorithm, they are actually working on this PD system. Yeah, so this is a basic introduction for this algorithm, but I'm gonna skip this one. I will mention, like, if we are going to use some of them, I will mention it in the following section. So, okay. So our first task is to find, if we know that equation 1 is already linearizable, our first task is to find a PD system, which tells us, which gives us all the possible transformation, like how they need to satisfy some PD, and and all the solution from this PD system is the possible point transformation, which will map the equation 1 to the linear one. So the Blumen-Komet equations is very basic for our algorithm. So assume now we have already have a point transformation, like which maps xy to the new variables t and u. And so if after change of these variables, you can rewrite the equation 1 to another, like this one. So actually this point transformation, they actually induces an isomorphism between the point symmetry algebras of these two ODE. And it can be expressed at the following. You can see like A, B is the symmetry algebra from the equation 1, and Xi and eta is the symmetry algebra for the new one. And in this equation, we should notice that even we have the new symmetry coordinates, Xi and eta, but they are still expressed in the old variables in x and y. Okay, so if we observe the algebra structure for the linear ODE, we find that in the linear case, the symmetry algebra, they always admit an n-dimensional abelian subalgebra, like we call it A, which is generated by the generators, like Xi and eta satisfy this condition. So the first coordinate must be 0, and the second one is a function of t, which means the eta is functional dependent with t. And so we can express the second condition in the Jacobian form. So actually, when n is greater than 2, we have this theorem 2. So equation 1 is linearizable if and only if its symmetry algebra admits an n-dimensional abelian subalgebra, like what we mentioned here. And the equation 1 is linear if and only if its generators in n-dimensional abelian subalgebras satisfy this condition we mentioned above. So now how we get the determinant, PD system for all possible point transformations is just in Maple, like for any input ODE. In Maple, we have the algorithm to give us a system for its the symmetry algebra. So we can use this system, and also the Bloom and Kume equations we mentioned before. And also together with these conditions, we just make a substitution in x, y back to that system and satisfy this condition. Then we can get the PD system for all possible linear mappings. So the final obstacle here is like how we get this A. You see, because this A is just a sub-algebra of the symmetry algebra, not the whole symmetry algebra. So like I said before, for any input ODE, we can always get the determinant system for the symmetry algebra. And moreover, like in Maple 2020, they add a new package called the algebra of vector field package. And it provides us some powerful tools to construct the derived algebra. Of course, it's the determinant system for derived algebra. And even the structure coefficient. And also, they can get the radical of R from the symmetry algebra by means of leaf decomposition algorithm. So, which means we can get what we need from this already exist algorithms. And so by case by case, so the case by case study, we have if the dimension of the L is one of the n+1 and n+2, we just simply have this sub-algebra equals to the derived algebra. And in another case, the trivial case, if the dimension of L equals to n+4, actually this sub-abelian algebra equals to the derived algebra of the radical. So since now we have the way to get the determinant system of A, and we can have the PD system for all possible linearizing map. Okay, so our next algorithm is about, for this special case, for the dimension equals to n+2. So we know that in this case, the linear ODE could be with the constant coefficient, like this one. So our goal is to output the characteristic polynomial of this linear ODE with constant coefficients. And in this algorithm, we don't need to compute the PD system for the linearizing mapping. We don't need any information about this, and just get the characteristic polynomial. And here we write it in the form like in a distinct roots for this polynomial with the multiplicity like ni. We need to notice that since this case is not a trivial case, so there are at least 2 distinct roots. A simple fact shows that after the rescaling of the variables, like we can change this characteristic polynomial to another one. This one, with the 2 arbitrary constant alpha and beta. And in this new characteristic polynomial, we see that it's just compared to the old one, it's just the scaling and transform of the old roots, and they still have share the same multiplicity. So which means no matter which polynomial we gave as the output, all of this result, they are equivalent up to some point transformation. So, like as we mentioned in the last section, in this case, the abelian subalgebra is just a derived algebra. which is spent by the operators or generators. Like, actually, all these generators is just the fundamental solution of the system. You can see we have a very clear form like this, ordered like this. So if we add, so we know that the whole symmetry algebra is in dimension n+2. So now we consider how it happens if we apply the other two generators on this derived algebra. The first one is this shift generator, the n+1, x n+1. If we apply this generator, which means we get the Lie bracket with the other generators in the derived algebra, we have upper triangular form. This is very easy to see from the properties of these fundamental solutions. So if you apply this operator, it's just computing the derivatives respect to t. And for the second generator, this one, it's a scaling generator. If we apply this generator to the derived algebra, it actually gives us the identity map. So yeah, so this based on these two facts, if we set like x bar is any linear combination of x n+1 and x n+2, and apply this x bar on the derived algebra, then the matrix we get is obviously in this form. We only need to care about the diagonal forms, because what we need is the characteristic polynomial. Okay, the last fact we need to use is that, so we already know this derived algebra is abelian, which means if we add any tail to x bar, the tail is from the derived algebra itself. So when you take bracket, since it's abelian, the tail will not influence the result, and I mean the coefficient, like the structure constant, will not change. So if you still apply this x bar, this matrix remains the same. But we need to know that in practice, like if you apply some algorithm from Maple, the structure, they give us the structure constant Cijk from a messed up basis, because it's not the algorithm is not to operate on the algebra itself. It's operate on its determining system. So this constant coefficient is actually change like all the time if we change the initial data. So which means that the basis we actually have for the algorithm is not like looks as concise like we said before. But luckily, since they are still the basis, so which means they just times some non-singular matrix, and for the similar matrix, they have the same characteristic polynomial. So we just have the following like easy way to get the characteristic polynomial. It's just we pick, so this this structure constant is a cubic matrix, and we pick one slice from them, which is a matrix, and we need to requires that alpha is non-zero, because we don't need the trivial one. And so, as it's very easy to exclude the wrong result, because you just need to compute its derivative and compute the common factor, and it's an easy way to know if this polynomial has only one root or two distinct roots. Since it's a basis, if we choose slice by slice, there always be one that the alpha is non-zero. And then we can compute this characteristic polynomial. And so we achieve the goal. Okay, so the rest of the presentation is just something about the generalization. The context transformation is the generalization for point transformation. And we can see that in these transformations, we involve the first derivative as well. So the new variables, like capital X, Y, and P, they will satisfy the satisfy the transformation condition. Like the first one is just the definition of the context transformation, but we know that actually all of the variables, they are just there are only one independent variable, is X. So which means like the capital Y, capital P is still a function of X. So if we use the total differentiation, we have another expression for the capital P. So this context transformation only needs to also needs to satisfy the another condition, which is the last condition in this slide. And here is the very simple example for context transformation. Actually, these two theorems make it possible to generalize our algorithm for point transformations. Because as we can see, if the order of the OD is 3, we only need to case-by-case study. And then we can know the contact symmetry algebra structure. And when the order is greater than 3, the theorem 4 tells us there's non-trivial contact symmetries, which means all this transformation is still the point transformation, which means from this previous slide, we know that is actually we have a capital X, the partial derivative of capital X respect to P is 0. So it, which means it's just simply a point transformation. So with these theorems, our algorithm for point transformation is that can be generalized to the contact case very easily. And the last generalization is actually our future work. We want to generalize the algorithm for the system of the ODEs, and we want to start from the 2 ODE system. From the previous references, we know that actually they classified all the symmetry algebra for this 2 ODE system. And they have, I think, more than 30 cases. But if we want to apply our algorithm, we only need to classify them in 5 groups. And we can see also here, the A denote the abelian subalgebra, which is generated by the fundamental solutions. So here the task is the same, like how we construct this A. So as we can see, there are 5 cases. If the dimension of the whole symmetry algebra equals to 5 or 6, then A is just the derived algebra. And if n equals to 7, we have 2 different cases to get A. Also for 8, we can see if like for 8, how we get 8 is not just by computing some bracket. It's but this algorithm is about computing the transport, which is also provided by the left package in Maple. And the last case is n+15, is just for the trivial case. Okay, that's it. Thank you.
Thank you very much. Other questions, comments?
Yeah. What can you say about the possibility of extending your methodology to scalar quasi-linear partial differential equations? For example, Bartzos equation, but it has a known analytic solution, but there are also Bartzos, Korteweg, and De Vries equations and other known equations describing the waves, so solitary waves and other waves. What do you think about that?
I think the possibility is not very big, because for most PD or PD system, the symmetry algebra is infinitely dimensional.
This leads to mathematical difficulties. Is it impossible to consider some particular cases with finite dimension?
Yeah,
dimension. Not?
I think for finite cases, maybe there's a big chance to generalize. As long as it depends on their symmetry algebra structure.
Mm. Okay.
Welcome.
Other questions? So, Zoom participants? So, if not, then let's thank the speaker again. And that was the last talk of this morning session.